Recording is rolling. It is Wednesday, October 30. We're going to continue these textbook puzzles. Which, guys, what do these textbook puzzles do? Friday. And I want to do all of them with you guys in class anyway. And yesterday, here's what we did yesterday. We did these four from chapter 6. You guys remember chapter 6 in your book? There's two halves. There's the projectiles, which we didn't look at because we did this a long time ago. Then there's the circular motion centripetal force questions. We did four out of those, 4 out of the 5. So we're going to do this one here, which has to do with the Earth rotating. And then we're going to switch over to chapter 7. I have 5 questions circled here. We should be able to do most of these in class today. And then by the end of class, you'll have almost all these done. So we'll see what to do with the last 1 or 2 tomorrow. It's number 74. Early skeptics of the idea of a rotating Earth said that the fast spin of the Earth should throw people off the equator into space, right? So, hey, how can we possibly be on a spinning Earth? Like, wouldn't that just like throw you up into space? Right. So let's throw some numbers at it. The radius of the Earth is 6.38 times 10 to the third kilometers. Guys, pause right there. If we're going to do some calculations, what unit do you want for distance? You don't want kilometers. You want what? Meters. Guys, how many meters are in 1 kilometer? 1,000. You guys know kilos 1,000, right? I'm going to jot that down because this question is still coming up at this point in this class. Guys, 1 kilometer is 1,000 meters. When you see lowercase k, that means kilo, which is a prefix for, well, a multiple of 1,000 or something. You'll see that out in the wild, like out in the real world. At some time, I can almost guarantee it. At some point, you're going to see k is an abbreviation for 1,000 of something. Okay, so let's look for that. 1,000 grams into kilogram. All right, so just hold on to the idea. We'll need that later. Show why this idea is wrong. Like the idea of you would be thrown off into space because the Earth was spinning by calculating the following. And we'll go to, so a 97 kilogram person at the equator, what would the speed be? What was the force needed to accelerate the person in a circle? What's the weight of the person? What's the normal force of the person standing on the scale? So again, being at the equator, we'll do those one by one. So 74, 34, right? Maybe I'll have this picture in my mind of here's the Earth. It's got a north and south pole, north pole, south pole. There's the axis of rotation. It's got an equator. Maybe you could look approximately like that, right? North, south, all there, right? And the Earth is rotating at some angular velocity. I'll call that omega for angular velocity. It's rotating. Okay? Then any point on its surface, except for the very north pole and the very south pole point, has some eastward tangential velocity. And it's fastest at the equator. I'll call that v. Right? While you guys are writing that down, where's my, here it is, here it is. All right, I want to remind you guys, I'm making some connections here. You guys remember between a turntable rotating at some number of radians per second and some location from the center r? If you multiply those together, you get its tangential velocity, like speed meters per second, right? We're going to have to do that. Okay. Oh, this Earth has some radius r. I'll label that here, r for the radius of the Earth. Okay. And then eventually we're going to have a guy standing on a scale. So here's a scale on the equator. This guy's standing on the scale at the equator, going around the Earth. Okay. Okay. Have I mentioned before the Earth is spinning like almost 1,000 miles an hour to the east? Right. When I say that, that's going to be one of the questions. Actually, it's coming up pretty soon. Okay. So, I threw a bunch of puzzle pieces around. We've got a bunch of questions flying around. Let's enter into this here. Guys, who could tell me how fast is the Earth rotating? One rotation. There you go. That's what I'm looking for. Every 24 hours. There you go. Right. Now, a little side thought here. If you also consider the Earth is revolving around the sun, it's not exactly 24 hours. I think it's like 23.9 hours. We're going to ignore that. Just call it 24 hours. Right. Right. But guys, if I'm doing some math with this number, which I do have to do, how fast is the Earth spinning? That definitely matters. Right? I don't want rotations per hours. I want what per what? Radians per second. Exactly. So let's do a conversion. Omega equals, you guys ready to do a conversion? I know it's 1 rotation every 24 hours. True, right? But I need to convert that to radians per second. Oh, look, I'm opening up some railroad tracks. Railroad tracks time. There's one rotation is how many radians? 2 pi. I got 2 pi radians right here. Right? Right. Now for the time unit, because here's what happened to rotations. I got radians per hour. I want radians per second. There's 1 hour is how many minutes? 60 minutes. And then 1 minute is how many seconds? 60 seconds. All right, there's my full railroad tracks table, and it's squeezed in a little bit, but you guys can read that, right? Okay. All right. What happened to my units? I got radians there. I got seconds down here. Hey, that's like radians per second. Look at there's these. Radians per second. Okay. Calculator time. Guys got calculator. All right. Let's multiply across the top, divide across the bottom. Let's see how many radians per second is the Earth rotating. So I got a 2 pi up there in the top. Then divide by. Now, guys, there's a bunch of stuff in the denominator. So after I hit divide, I'm going to open a parenthesis. Make sure it's all grouped together. Got 24 times that 60 times this other 60. All right. All right. All right. So you guys caught up to where I am? Maybe you have a picture that could be helpful. You guys got this conversion table. We're going to get what is the angular speed in radians per second, which your book didn't actually prompt you to do, but we do have to do this as a middle step. This is an important step to do. All right, what am I getting here? All right, are you guys getting this number? 0.0000727? Are you guys getting that? Guys, that's, what unit is that? What unit? Radians per second, right? Hey, who remembers how do you write that in scientific notation? Yeah, 7.27 times 10 to the negative 5. And that's still radians per second. Okay. So that number, same number. So as we're doing calculations going forward, how do you want to type that in your calculator? Well, just pick your favorite one because they're the same thing. Okay. Right. Question A actually said, what's the speed of the person at the equator? Right. Now that's a little bit ambiguous, speed. This is the angular speed, so that could sort of be the answer, although you wouldn't have to be at the equator for this to be true. Because this is the angular speed no matter where you are on the surface. If you're like up with the polar bears, or down here in Florida, or down here on the equator, everybody's rotating that fast. All right. Well, let's get a linear speed though. That's probably what they're trying to apply. Linear speed. Guys, how do you go from angular speed to linear speed? You have to multiply by the radius, right? Here's how fast, say, a turntable's turning. Guys, instead of a turntable turning, could this be the entire Earth spinning? This could be the North Pole. We're looking straight down. Right, straight down. I guess we're okay. Right. We're in Santa Claus's sleigh. We went straight up into space. We're holding our breath. We're looking straight down. Here's the Earth spinning. Right? And hey, here's the equator out on the edge at 1 Earth radius away from its axis of rotation. If you know how fast the Earth is spinning in radians per second, which we just got, and you multiply by the radius of the Earth, you can get a linear speed at the equator. Can you guys do that? Right. See if you can stay a step ahead of me. Omega times R. Right. If you can stay a step ahead of me for, well, any time in the class for any question, that's a good sign that you can figure this out. So in place of omega, I'm going to plug in this number. 7.27 times 10 to the negative 5. That's radians per second. And for the radius of the Earth, now, did they give you a radius of the Earth here? Yeah. They put it in kilometers. Because they gave you 6.38 times, they said 10 to the third kilometers. Guys, 10 to the third kilometers. That's 10 to the how many meters? A factor of 1,000. Guys, 1,000 is how many zeros? 3. If you have 10 to the 3 and you need 3 more zeros, that brings you up to 10 to the 6. Yeah, 10 to the 6. Right. And now we got meters. Right. How about this? Meters per radius, if you like, because we're talking about the radius of the Earth. Meters per radius. So that right. This is going to give us some number of meters per second. That's what I'm trying to figure. Right. Meters per second worth the units. Let's multiply together. Oh, well, here. I got the angular speed right here already. So just say times 6.38 times 10 to the 6 meters. Because the radius of the Earth is like more than 6 million meters. That's what 10 to the 6 is, million. Right? So multiply that all together. I'm getting, I'll call this, the number on my screen is about 464. Okay. All right. And make sure you guys know what this means. Guys, that's 464 what? What unit goes right here? Meters per second. That's right. Meters per second. Okay. That is the tangential speed of the equator of the Earth. Right? So if you're standing on the equator, you're moving that fast relative to the axis of the Earth. Okay? That's ignoring the Earth also revolving around the sun. We're just focused on the Earth spinning on its own axis. Okay? By the way, if you convert this to miles per hour, I'll just give this to you guys because, well, a little bit short on time. This is approximately 1,000 miles per hour. It's a little over 1,000 miles an hour. And then if you change your latitude as you go further north, it'd be a little bit less. But up here in Florida, maybe it's in the, I'm going to guess about 900 or something like that, miles per hour. Right. But there it is in meters per second, which is what we care about for this class, metric. Right. All right. So you guys got the linear speed of the Earth. That's question A. That's question A right there. All right. You guys ready for question B? Question B. What force is needed to accelerate the person in a circle? So how much force would be necessary to keep this person on? Now, this is definitely a circular path, right? The equator of the Earth as he's going around. Right? So how much force do you actually need? Right? So 74B, is that, yeah, that was A, we just did. We did part A, boom, done. Okay, question B, how much force? Guys, in general, how much force do you need to keep on a circular path? And it's a fraction. What goes in that fraction right there? So how's that go? MV squared over R, is that what you said? Yeah, MV squared over R, right? Okay. So let's do MV squared over R. Okay. Now, what numbers are going to feed in here? So this is the force necessary to keep you in a circle. I'll call this a net force. That's what this is. So I know centripetal force, MV squared over R. It would be a net force to keep you on a circular path. Right? Oh, they picked some 97 kilogram person. So I'm going to put 97 kilograms in for the mass. 97 kilograms. Right? Ooh, V. Hey, could that be this right here? 464 meters per second? We're going to square that. Divided by the radius of the Earth is 6.38 times 10 to the 6 meters. Okay, I think that'll do it. That's good. That's gonna do it. Here, I'm gonna divvy my paper. I meant to divvy it in half anyway, but I'll just write something else down here. Here's a different perspective on this. Centripetal force. Do you guys know an alternate formula for centripetal force? Do you guys remember? I know I don't have the answer yet, but all right, I'm going to leave it blank there. I'm going to come back to that. Do you guys remember O'Neill cylinder? You guys remember this? Right? Could I have done this right here? It should also give me the correct answer. I want to check that. I'm going to do this 2 different ways. Do MV squared over R, which is all set up right there. I'm also going to test M omega squared times R. I want you guys to see that this is going to give me the same thing. So I still got the same 97 kilogram person. The omega for the Earth, well, that's this number right here, 0.0000727 rad per second. 0.0000727 radians per second. Okay, I got to square that angular speed. And the radius of the Earth is 6.38 times 10 to the 6 meters. All that, right, equals, right. All right, so I got 2 different approaches to get what force would keep you on a circular path of the equator. I wonder if I'm going to get the same number. And how big should that number be? So let's do 97 kilograms times 464 squared, and back up to this one here, right? Divided by, and then in parentheses, 6.38 times 10 to the 6. That's how many meters radius, right? Okay. Are you guys caught up to where I am? Again, I have two separate setups, but they should give me the same answer. So we got from the linear speed point of view and from the angular speed point of view. All right. Now, before I hit enter, I want you guys to kind of reason in your mind, think how much force should that be? So here's the premise. The Earth is spinning. You're standing at the equator. The Earth is spinning. And if there was no force, you would kind of fly off into space. So there has to be some force pulling you down. In fact, that's what we're about to calculate right here. How much force do you think is necessary to hold a 97 kilogram person on the surface of Earth as the Earth is spinning? Do you think it's a lot of newtons or a few newtons? Are you guys ready for the answer? Actually, I bet some of you guys already have this in your calculator. Who knows the answer? Who's got it? Did you say 3.27 newtons? Oh yeah, that's what I'm getting right here. 3.27 newtons. Oh yeah. Right. Guys, 3.27 newtons. What is that in context? All right, here's one of your lab masses. Guys, this lab mass says 100 grams is stamped into it. 100 grams. How much force does it take to lift this up? 1 Newton. There's 1 Newton force. Guys, if you had, about 3 or 4 of these, that's all you would need to stay on the surface of the Earth. That's it. Right? Or how about this? Here's 1 kilogram. How much does this guy weigh? 10 newtons. Right? You don't even need this to hold a person to the Earth. You don't even need this. Right? You need some force, but it's really an amount that you could even pick up. Right? Let's check from the angular speed point of view. So I'm going to go 97 kilograms. I'll do 0.0000727 radians per second. I'm going to square that. And then multiply by the radius of the Earth, 6.38 times 10 to the 6 meters. Okay, and out pops. Hey, it's the same answer. 3.27 newtons. Same thing we got before. Look at that. And I just wanted you guys to see that would be the case. Be the same thing. All right. So you guys good on part B? All right. Oh, there's more. Question C. What is the weight of the person? Because weight, isn't that like a gravitational force? So 74 part C, weight. Oh, guys, could that be, here, give you guys 2 perspectives. M times G or capital G, M on R squared, right? Could this be the same thing? Right. See if you guys are following. I'm going to dash outline part of this. Let's see. I got a gold pen right here. Let's do gold ink. You guys see that part I just dash outlined in gold ink right here? This GM on R squared bit? This bit right here? Is that? What is that equal to? What does that represent physically? Just the GM over R squared bit. And I think you guys did this calculation a few days ago for the Earth. Like, capital G is universal gravity constant. That's the 6.67 number, 10 to the negative 11. Here could be the mass of the Earth, for example. Here could be the radius of the Earth that's being squared down here. If you put that in your calculator, GM over R squared for all Earth values, what do you get? 9.8 meters per second squared. Because that part I just dashed outline is the gravity field. It's the same thing. That is that. You see it? And then here's the mass of the person, which they're identifying as 97 kilograms. It's just some guy. Okay. All right. So it doesn't matter how we do this. We'll get the same thing. Weight. Okay. There's actual gravitational pull. Well, let's go 97 kilograms person. Let's go ahead and do 9.8 meters per second squared. All right. Again, if you wanted to rederive that from the universal gravity constant, you could do it that way too. I'm just gonna kind of skip back past that. Got so much class time. You would get the same number. Doesn't matter. All right. So what are we gonna get here? 97, 98. I'm looking at 950.6 is the number on my calculator screen. Now that number has units attached to it. What's the unit? How do you measure weight? How do you measure a force? Newtons. That's right, newtons. And it's also right here anyway. Guys, kilogram meter per second squared. That's a Newton. All right. So here's the weight of the person. Ooh, compare that to the force that would be necessary to keep them on the surface at all. Guys, this guy weighs 950 newtons. The necessary force to keep him on the ground is only 3 newtons. Whoa. Is this guy anywhere close to flying off the face of the earth? Nowhere near close. Okay. Now there's one more question, question D, which is an interesting context here. It says, what's the normal force of the person, say their apparent weight, if they're standing on a scale? Show this guy standing on a scale. Scale. Here's this guy standing here. Remember, he's at the equator. They're spinning the whole deal. Here's the center of mass. Right. Let's do a FBD, free body diagram. You guys ready for this? All right. All right. You guys have done plenty of these type before. Here's what force is pulling this guy straight down. Yeah, mg, which is, oh, we just got that. That's 950.6 newtons. Okay, I got that. Okay. What force is holding him up? The normal force. Okay, now here's where there's about to be a twist. Last week and all the way up to last week, I've been telling you guys that the normal force is how big compared to the weight if he's just at rest? Same size, right? But hang on. I think I've been lying to you the whole time. That's not exactly the truth, because this guy isn't really at rest. He's actually moving on a curved path because the Earth is spinning, isn't it? You guys see that dashed outline right there? Path? Now that's really exaggerated, but that could kind of represent, say, the equator of the Earth. Right? Exaggerated. Right? He's moving on a curved path. So which force is actually bigger? His weight down or the normal force up? Which is bigger? Here, guys, if you're moving on a curved path, the way I drew the curved path, he's moving on a curved path. The overall net force has to be which way? Down, because that would be towards the center of what would be a circle. Like, yes, cut through the Earth, that'd be a circle, right? Pretty much. Okay. So I think I should draw this normal force as a tiny bit smaller than the weight. I'm going to draw it exaggerated a little bit, where it's obviously shorter. You guys see the normal force is shorter than the weight? Okay. Now, it's almost the same, but it's a tiny bit different. We're going to see what is that. Yeah, we're going to put this in context. Okay. So could you guys say that the net force on this guy is equal to his weight pulling down minus the normal force from the scale holding him up? Is that true? Right. And guys, what is that net force equal to? How many newtons? 3.27, right? Right. Guys, there is an overall net force pulling down of 3.27 newtons. That number right there, right? It's not zero, because the Earth is not flat. The Earth is not stationary. It's a ball and it's spinning. He's moving on a curved surface. That net force, right? His weight, his true weight is, well, this number right here, 950.6. That's newtons. Right? I'm going to subtract off the normal force reading on the scale. What does the scale say? Can I just add this over, subtract that over? Here, I'll do this right here. 950.6 minus 3.27. The normal force reading on the scale is 947.3 something newtons. There you go. There's the answer. There's the reading on the scale. Right. So while you guys are digesting that, writing that down, thinking about this, right, recap what's actually going on. This guy on the equator steps on a scale. The scale reads how much? How much does the scale read? 947 newtons. Right. So this guy says, oh, I guess I weigh 947 newtons. But that's not exactly true. How much is the Earth actually pulling down on him? More like 950 newtons, right? The scale says 947. His actual weight's 950. Do you guys see there's a difference of 3 newtons to keep him on a curved surface? Okay, right. What is that as a percentage? Like when you step on a scale, that scale is going to be slightly, ever so slightly different than Earth's gravity force. I bet you're probably not 97 kilograms, but I bet it's the same ratio. Right? Let's see, what is that ratio? I'm going to just write the word ratio. You guys get the idea. The ratio of the normal force reading compared to your actual weight. Right? Because last week and before, we've always been saying, oh, it's a 1-to-1 ratio. Today we're saying, that's not exactly true. What's that ratio? What's that number divided by 950.6? I'm getting 0.9966. Can I interpret that as like 99.66%. Right? 99.66%. So when you step on a scale, and that scale tells you your weight, what that scale is actually telling you is 99.66% of your weight. And that's assuming that you're at the equator. Okay. Well, the difference then is less than 0.5%. So it's kind of a rounding error. Okay. All right. Guys good? All right. So that one's fun. You guys ready for the gravitation questions? Almost. All right. It's about to be gravity time. Number 58. Assume you have a mass of 50 kilograms and Earth has a mass of 5.97 times 10 to the 24 kilograms and a radius of 6.38 times 10 to the 6 meters. Great, got all that. Two questions. What's the force of gravitational attraction between you and the Earth? And question B, what is your weight? Wait a minute. Are those the same question? I think those are the same question. Kind of like I think we just talked about this a minute ago. 58. You can say force equals, now universal gravity attraction is G-M-M over R squared. Your weight is just mg. Right? But here, this is what I was saying before with the Golding. I'll do Golding again. This lowercase g is gm over r squared. It's the same thing, isn't it? Say same thing. Okay. So here, since they gave you the mass and radius of the Earth, let's do the universal form of this. Okay. But this is your weight. So, well, I'll say weight. I could just say weight equals capital G is at 6.67 times 10 to the negative 11. Okay. Newton meter squared per kilogram squared. Some units. Mass of the Earth. Call it 5.9. What does it say? 5 point. Okay. Your textbook says 5.97 times 10 to the 24 kilograms. Right. Sometimes I've seen 5.98. Sometimes I use that. Right. And your own mass, number 58 says use 50 kilograms. Suppose your mass is like 50 kilograms. Right. Then all divided by, the distance between you and the center mass of the Earth is the radius of the Earth. That's why we can use that right here. 6.38 times 10 to the 6 meters. That's like 6 million meters. And one more detail, because I'm leaving off one thing. What am I forgetting? Square. Aha. Okay. That's going to be the answer. Okay. Now, before you go plugging and chugging, maybe you can kind of play off this mg over here and kind of remember, guys, if you have a mass of 50 kilograms, how much approximately do you weigh in newtons? Huh? 500? About 500 newtons? That's if you use 10 meters per second squared for G. Wouldn't that be true? 50 kilograms weighs 500 newtons, right? Oh, next detail. That 10 meters per second squared, that's rounded a little bit from 9.8, isn't it? So do you think this, when I punch it in my calculator, is going to be a little bit less than 500 newtons? Maybe about 490, maybe? I'm going to guess this is like 490 newtons, right? Right, so final part. Can you correctly plug that into your calculator? Okay, so good. Definitely pull out a calculator right now and try this out, because lots of students have trouble plugging this correctly into the calculator. So see if you can do it. If you can't, then make sure you can. Right. Open parentheses, 6.67 times 10 power negative 11. Close, open. 5.97 times 10 power 24. Close, open. 50, close. Divide by, open. 6.38 times 10 to the 6, close square. All right. So as long as I didn't make any typos, again, I'm looking for maybe a little bit less than 500 newtons. I'm going to guess 490. All right. All right. You guys plugging that in? Yeah, so you guys, what number are you guys getting? 489? Let's see if I'm getting that too. Aha, it is. Aha, 489 newtons. Oh, yeah. Oh, yeah. And that's exactly what it should have been. Oh, yeah. All right, ready for the next one? Number 67. Mimas, one of Saturn's moons, has an orbital radius of 1.87 times 10 to the 8 meters. Can I call that 187 million meters, I think? And an orbital period of 23 hours. Right. Now pause right there. Because when they give you a time period in hours, and they're looking for a calculation, you're probably going to have to do what to that time first? Convert it to seconds. Yeah. Just hold on to that thought. Okay. Use Newton's version of Kepler's third law to find Saturn's mass. All right. Actually, I want to do a little bit extra with this one too. So 67 mass. Get, maybe here could be a planet, for example, Saturn. We got a moon going around some distance out. That right. We're trying to figure out what's the mass of this planet. Right. There could be maybe the mass of the moon, although that doesn't matter. I don't think I even told you that. Right. And there could be some radial size of that orbit. Right. All right. Now I'm going to find a couple of posters. I need this poster, this poster. All right, here we go. All right. So let me back up a little bit from a few days ago. You guys have seen both of these posters. One of them goes like this: orbital speed. Like, how fast do you have to go to stay in orbit, say around a planet? Okay. And the process went like this. So, well, stay in orbit, that sounds like you need a centripetal force provided only by the gravitational force. Here's centripetal force. Here's universal gravitation force. Then you can solve for V, and you get the orbital speed as this. Boom. Right. So if you know the mass of the planet, you can calculate how fast you have to go to stay in orbit. But you can also do this backwards. Hey, suppose you're sending off a bunch of space probes, pew, 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 and then they're orbiting, say, different planets or something. And you just by trial and error, figure out how fast does it have to go. Go a little fast, no, it's going too far away. Make it go a little slower until finally it sets up a stable orbit, a circular orbit. Do you guys see that in principle you could use that to calculate the mass of the planet? Okay. That's pretty much what they want you to do here, except they mentioned something else. They said actually use Kepler's third law. So, well, the Newtonian equation version of that, which is this box right here. Guess this? That's really kind of the same thing. So here's how much time to go around. Here's the distance. And then you could calculate this m here, which is the mass that's being orbited. In this case, the mass of Saturn. Guess that? Okay. I want you guys to see this. That this and this are the same thing from different points of view. Are you guys ready to do that? We're going to do a little extra. I want to prove to you guys that this is this. Okay? You guys ready? Because remember, Kepler just figured out this proportion. But you can't make that an equation until you bring in Newton. So let's do that. Let's start with orbital speed. Now, this has already been sketched out, so I'm going to start with this box. All right, let's do it. Let's do V orbital equals root G M on R. We'll start with that. Okay. Because this orbital speed calls V, orbital speed. Isn't that like distance over time? Distance over time? Right? Hey guys, what distance around a circle? What's that called? What's the distance around a circle called? Circumference. Ah. And isn't that circumference a function of this radius? Actually, I think you guys know a formula for that. Or the distance compared to time for speed, orbital speed, right? The distance around divided by the time period around, okay? Guys, what's the formula for circumference of a circle? Circumference equals 2 pi r. That's right. And the time to go around, I'm going to call capital T for time period. That's a common thing to do in physics. Capital T could be time period. Okay. And that could be equal to square root Gm over R. Right. Remember the M is, okay, what is capital M? Is that the mass of Saturn or the mass of the moon? Saturn. Yeah, that's the mass of what's being orbited, in this case, Saturn. Right. Right. So what next? Well, if I want to make this look like Kepler's third law, then I need to solve for T. You guys see that? Let's solve for T. Solve for T. Hey, can I dunk these both upside down? Do reciprocal? Let's do reciprocal. Time period divided by 2 pi r must be equal to square root of r over gm. Right? I just dunked each of these upside down. I can do that. Is that okay? Right. Cross multiply 2 pi r. So time period equals, I got a 2 pi r times square root r over gm. Right. Now we're getting really close. Right. This r and this r. Can I put those two r's together? I can. I have to figure out how to take this r outside the radical and put it inside the radical. Here, I'll have a little thought cloud over here. There's a little thought cloud. Oh. What is the square root of r squared? R, right? It's just r. Right. So if I have an r out here and I want to put it inside the radical, doesn't it show up as an r squared inside the radical? That'd be the same thing, right? If I combine that with the r that's already there and put them all together, now I have what? Okay, so I got 2 pi outside, I got times, I got a radical, I got a fraction, and the bottom is the gm. What goes in the top? R to the third. Because I got one here already, and I got this r on the outside, which looks like r squared on the inside. Put it all together, that's r and r and r. That makes r to the 3. You guys see that right there? Hey, that's Kepler's third law. Well, the Newtonian equation form of it. That's the same thing. Didn't we just derive that from orbital speed? Right? So I said I wanted you guys to see that this kind of is orbital speed. It's the same thing. It just, rearrange and solve for time. Okay. Anyway, they want you to solve for the mass of Saturn. You guys ready to solve for the mass of Saturn? All right. So I'm going to pick up from that point. I'm just going to write Kepler's third law right here. Just copy paste that. So 67 continued. Time period equals 2 pi times the square root of r cubed over gm. All right. So we're starting from there. And I want to solve for the mass of Saturn. Now, there's two ways you can go about this. You can plug in all the numbers first and then do the algebra after the fact. Or you can solve in terms of variables and then plug in the numbers after the fact. I'm going to do it that latter way because all these letters is real short. And all those numbers have a lot of scientific notation going on. They're either extremely small or extremely big. So it's actually, I think, easier to write it in terms of variables. Let's solve in terms of variables. This is probably a good skill to have anyway. Right? How can I solve for this m? What should I do first? Well, guys, how can I undo the square root? How do you undo a square root? By doing what? Squared. I'm going to square both sides. Let's do t squared equals 2 pi quantity squared. So it's like 4 times pi squared if you like, right? Times, and then the radical just goes away. I got an r cubed over gm. Trying to solve for this m, right? Now what I'm solving for is just very simply in the denominator, the square root's gone. Right? What's my next step? Cross multiply the m. Can you do that? Cross multiply the m. So now I'm getting m, I'm solving for, times t squared equals, I got a 2 pi, which is being squared itself. Right? I got a times r cubed. That's all over g. It's like that. What's the last step to solve for m? Divide down t squared. Right. So the mass of anything being orbited is equal to, as long as you have a circular path, right, it's probably pretty close. Right, so take 2 pi quantity squared times the distance cubed divided by gt squared. All right, this is going to get it for us. Actually, this is a good master equation right here. As long as you have an orbital path that's pretty close to a circle, right? Orbits are realistically slightly elliptical, but not that much, right? Then if you know the orbital radius, the time period, and the universal gravity constant, you can always determine the mass of whatever's being orbited. Boom. There you go. Right. So we're watching the satellite go around. We count how much time does it take to go around, plug that in there. We know, we can see its radial orbit, or the radial size of its orbit. We know G. Okay. All right, so did they give us some numbers? There's a 67 me mass. We got, here's the radius of orbit, boom, right there. Oh, there is one bit I have to go back and do though. We never actually did convert the time, did we? We gotta convert the time. So let's, here's what I do. I'm gonna convert the time right down here, and then on the next page, I'll plug this, plug the numbers in. So time period, here's when our time period was 23 hours. let's convert that into, well, you guys tell me what should I do? What's the next step? 1 hour is how many, what? Yeah, 60 minutes, we can do that. All right, do I want minutes? Nope. Do I want seconds? Yep. Are you guys getting 82,800 seconds? Right? Okay. So that's gonna feed into this time period right here. We know universal gravity constant from Von Jolly. And this radial size of the orbit was given in the premise of the question. So now we got all the parts. All we have to do is put it all together. All right, you guys ready for that? Okay. So next page. All right. So all I'm going to do is follow this formula right here and just plug the numbers in. So the mass of Saturn is, all right, got a big old fraction. I got a 2 pi quantity squared right here. The radial size, now this I have to pull off the page. It says 1.87 times 10 to the 8 meters. 1.87 times 10 to the 8, and that's meters. Now that's being cubed, so to the power of 3. Then divided by gt squared. So g is 6.67 times 10 to the negative 11. That's Newton meter squared per kilogram squared. And time period is 82,800 seconds. Right? One last detail. I'm going to throw some extra parentheses here. Okay, I think. Oh, wait, am I missing something? I am missing something. Oops. Guys, time what? Time to the power of 2. Yeah, squared. Okay, don't forget that too. Okay. All right, a few extra parentheses. All right, I think that should do it. That should tell you the mass of Saturn. Again, you're sending space probes around lots of different planets, just kind of trial and error, figure out how fast does it have to go. Then you can use exactly this method to figure out the mass of anything, like any planet. Right, so calculator time. Right, you guys type it, I'll type it. Let's see if we get the same thing. Right, no, be really careful with parentheses. That's part of the trick. So that's part of your school practice right here. Is can you correctly communicate this to a calculator? Got 2 pi quantity squared. Got the radial size. Put that in parentheses to the power of 3. Group all that together, then divide. Now, after I hit divide, I'm going to open up an excess of parentheses. If you have this model calculator, it'll naturally close the excess parentheses. Not all calculators do, right? But I definitely don't want to close parentheses prematurely because they got a bunch of stuff multiplied all in the denominator. Universal gravity constant and the time period, and then square the time period, right? I think that should do it for me right there. All right, before I hit enter, I'll give you guys a shot to get this first, see if you guys are getting the correct answer, and then I'll check and make sure, because I might have a typo too. I want to make sure I don't have a typo. All right, so you guys go ahead. You guys are writing this down. You guys are punch this into the calculator. All right, you guys are figuring out what is the mass of Saturn. All right, are you guys getting a mass for Saturn? Yeah. You guys getting a number? Also, while I'm walking around, anybody got any questions about anything? Is this all making sense? It's all working out? All right. All right, so what are you guys getting for the mass of Saturn? Huh. All right, well, let's see what I'm getting. Let's see if I punch this in correctly. Yeah, okay, this number looks right. It's, okay, I'm getting 5.65 times 10 to the 26. How many guys got 10 to the 26? Yeah, all right, winner. Right. And what unit? Guys, what unit is that? How do you measure mass? Huh? Kilograms. Kilograms. 10 to the 26 kilograms. Right. Now, here's how I know this number is right. Because like how could you know what the heck is the mass of Saturn? Right. Earlier today, one of my earlier classes, I had a typo and I got like 10 to the 23rd kilograms, and I knew that was wrong immediately. Guys, if I did a typo and I got 10 to the 23rd kilograms, how do I know right away that it has to be wrong? And 10 to the 26 is probably right. Because I can compare it to the mass of Earth. Guys, the mass of Earth is 10 to the what? 24. You guys remember the mass of Earth was like 5.98 times 10 to the 24 kilograms? Right? I think it says, we just used that earlier today. Mass of Earth is 10 to the 24 kilograms. Guys, if Earth is 10 to the 24 kilograms and Saturn is 10 to the 26 kilograms, Saturn is how many times the mass of Earth? What is 10 to the 26 compared to the 10 to the 24? 100 times. Yeah. That's 10 to the 2, which is like 100 times. Yeah. And 5.65 is 5.98, 5.65. That's almost the same number. Saturn is about 100 times the mass of Earth. Okay? Yeah. And if I got 10 to the 23, that would be saying it's less massive. So that's how I knew it couldn't be 10 to the 23. That would make sense. All right, guys, ready for 71? 71. Satellite. Hey, geosynchronous satellite. Guys, break down that word, geosynchronous. Geo, as in Earth. Synchronous, as in if things are synced up, they're moving together. So like moving with the Earth. Hey, guys, what do you think a geosynchronous satellite means? Like to make one trip around the Earth, one orbit, it should take how long? 24 hours, you guys think? Right? Yeah, exactly. That's geosynchronous. It's rotating as the Earth is spinning. Okay. Appears to remain over one spot on Earth, as shown in this figure. Yep, that would also be true if you're standing on the Earth and looking straight up in the sky and you see that satellite. It looks like it's hovering over you all day, every day. Like, that satellite isn't moving. It is moving, but it's revolving as the Earth is rotating. Right, it's not moving relative to you. Right? Assume a geosynchronous satellite has an orbital radius of, I kind of wish your book didn't do this, but they kind of spoiled it. They told you exactly where to park the satellite to make it geosynchronous. They said 4.23 times 10 to the 7 meters. Right? Maybe I would have asked the other way around. It's like, where should you put the satellite? That's the answer. Now, the question is, what's the speed in orbit? Like, how fast is it going? And then look at question B. Calculate its time period. Now, since I'm saying they're kind of asking this backwards of how I would have asked it, what does the answer to B have to be? 24 hours, right? What's the time period? It's 24 hours. All right, but we're going to do that. We're going to sort of confirm that this is, in fact, geosynchronous. Boom. All right, so 71, geosynchronous. Here, I'll write that word down. Looks bigger for the camera. Geo, hold on. Can I spell? Oh, no. So many letters. All right. And so what they give us here, I gave you an orbital radius of 4.23 times 10 to the 7 meters. Is that all you need? I think so. Yeah. All right. So question A, speed and orbit. Is orbital speed, could that be distance compared to, hold on. Never mind. Scratch that. I'm going to do this a different way. Pretend I didn't say that. I was going to say distance over time, but you'd be plugging in 24 hours. I'm going to do something a little different. Let's do, let's do this one right here. You see orbital speed? Okay. But to do this one, you actually need 2 more numbers. I'm going to write them down here. Let's do gravity constant is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay. And also the mass of the Earth is, let's do 5.97 times 10 to the 24 kilograms. Sometimes I say 5.98, but our book's saying 5.97, so let's do that. Okay. Let's say that all these 3 values are given values. Okay. So we have those 3, this, and this. We have 3 given values. Okay. And let's cut straight to orbital speed is square root gm on r. Okay. Because you guys remember how you derive that. It's exactly what you're looking at right there. It's how you derive that. Boom, boom. Okay. And what was the question? Oh, calculate speed. Okay, so this is set up to solve it anyway. Okay. You don't even need algebra at this point because that's already taken care of. just arithmetic. We're just going to plug everything in. You guys ready to plug everything in? Orbital speed is square root. You got a fraction in here. Here's universal gravity constant. Here's mass of the Earth. And here's the radial size of the Earth. Or sorry, not the radial size of the Earth, the radial size of the orbit, which is this number they gave you here. 4.23 times 10 to the 7. Now that's meters, but I'm going to take all my units outside. Okay. Notice I didn't write any units yet. I'm going to bring it out here. And guys, what unit is this going to give right out here? Meters per second. Yeah, because it's speed, meters per second. Okay. All right, all good so far. Good so far. All right, calculator test. Can you plug that into your calculator? Let's see if we all get the same number. So, here, give you guys a little hint. When you type square root, if you have the same model I do, which I think you do, because got a class out of these, it gives you one parenthesis, but be careful. As soon as you close the parenthesis, stop square rooting. I see a bunch of stuff under that radical. So to be safe, I'm going to open up an excess of parentheses. Aha. Then gravity constant, mass of the planet, divided by radius of the planet, or sorry, radius of the orbit, I meant. Radius of the orbit. Okay. Boom, boom, boom. Did I type that all right? I think that's right. All right. Are you guys getting an orbital speed? All right. What are you guys getting for orbital speed? And you know what? Well, before I hit enter, while you guys are catching up to that point, let's think a little bit. Like, what should a reasonable number for this be? Like when you get a number on your screen, how would you know if it's right or not? Well, how about this? Here could be the Earth. Do you guys remember if you're on low Earth orbit, so you're like just above the atmosphere, how fast do you have to go to stay in orbit? What's the past tense of eat, gang? 8 kilometers per second. You guys remember that? 8 kilometers per second? Well, now, if you back up and you're further away, geosynchronous is like way out here. Do you have to go faster or slower if you're way away from the Earth? I bet it's slower. I bet you don't have to go as fast to stay in orbit. So I bet this number has to be less than 8,000. You guys get that? Let's see what. I'm getting 3,000 something. Are you guys getting 3,000 something? Yeah, I think that number definitely looks reasonable. So I can be happy with that. You guys happy with that? All right, let's do one more thing today, which is question B, calculate its time period, which you guys know what the answer is going to be. It's got to be 24 hours. We'll do that, and then that'll take us to the end of class. So let's get the time period. Now, here's where I scratched out an equation. I'm going to go back to that. Speed is distance compared to time. Okay? We're solving for time. So, guys, is time just distance over speed, like that? Right? And isn't that like 2 pi r over v? Right, is time. Right. So let's do 2 pi. We got a radius of 4.23 times 10 to the 7 meters. Remember, that's an orbital radius. And the speed is 3,068 meters per second. Right, meters over meters per second. That's going to tell us time in seconds. Let's do one more thing. Guys, conversion. I got a little railroad tracks here. This is going to tell me how many seconds. There are 3,600 seconds in 1 hour, right? 60 times 60, right? So I'll divide that down, but that should tell me how much time. Let's see if I did this right. 2 pi times r divided by, and I got 3,068 and 3,600. All right, come on, please be 24. It's gonna be 24. Oh yeah. 24 hours. That's right. Bing. All right, that's a good pause point today.